All right, so the webinar, I'm going to turn off my, hopefully I can do that. Yeah, I want to turn off my video just because I've been having trouble. Zoom has been that's not like my webcam. So I'll turn it off until we have the questions at the end. Okay. Right, so this webinar is about the TGE maps in DR3. So TGE stands for Total Galactic Extinction. And essentially, these are two-dimensional maps. Here's one of the maps I'll be talking about. So the Total Galactic Extinction map is a 2D extinction map organized where the sky is divided up by heliopics at different levels. So we have actually more than one map. We have maps at multiple resolution, as I'll show here in a moment. And it's a map of an extinction parameter A0. And I'll explain what that is in a moment here. So to map extinction in the galaxy, the idea of the Total Galactic Extinction Map is to give a measure of the foreground extinction of the Milky Way for extragalactic objects. This was the original goal of the processing. So to do that, we pick extinction tracers. In particular, we choose giants that are outside of the ISM layer, so above at least the 300 parsecs from the galactic plane. And why A0? So A0, as I just mentioned, is a monochromatic, is a extinction parameter. It's the monochromatic extinction at 541.4 nanometers. And it's one of the parameters in our adopted extinction law, which is for Fitzpatrick 1999 for DR3. And A0 measures are taken essentially from the A0 and TGE is based on the A0 measures taken from GSP fault, which provides APs for individual sources. So we first find the giants in the heliopics and that are outside the galactic plane, and we just take the median, their median A0 values. Very simple. So here later we'll be sharing the slides. These will be links to the paper that explains more details in terms of the method, and also a link to the online documentation, which has also further details in terms of how the map was constructed. So in terms of why A0, instead of say AV or AG or something else. So the problem is that extinction really depends on the source spectrum of the star. So because of the wavelength dependence of the extinction law, it will, as you increase the reddening, you're modifying essentially the spectrum that's arriving at as you're going down the line of sight. The flux spectra is changing. So here, if you wanted to calculate the flux in the G band, you have to take into account the passband of G, and this incident flux then is moderated by the source flux, the source spectrum, flux from the star, moderated by the extinction law, A lambda. And so if you want to calculate then an extinction, what you really need to do is you need to take the ratio of these two fluxes, that is the flux from the source without extinction, okay, that would be capital G, divided by the flux from the source that has extinction though. And this is the same for G band or any band. So here on the left-hand plot, just to show both the dependence of the extinction in the G band as a function of the temperature of your source spectrum and as a function of the amount of extinction. So you see that it's nonlinear, okay, first of all, and that there's a strong dependence on the underlying source spectrum with the temperature of the star. And the reason why this is so obvious in the G band is because the G band is a very wide pass band. If you go to a narrower flat pass band, these dependencies start to become less and less. So here on the right, you see a plot of AV versus A0, and you can see that at moderate extinction values, they're almost the same. In fact, the ratio of AV to A0 for cool stars is about 0.98, so quite close to 1. And it's very nearly linear. You only start noticing it being nonlinear at very high extinction values. So the reason why A0 gives you, because it's a monochromatic extinction, it doesn't have this dependence on the source spectrum and so you can essentially provide a map, an extinction map that's valid for any star only if you use a monochromatic extinction parameter, which is what we're doing for TGE. Now that does mean that there's an additional complication is if you use the extinctions from TGE, then you're going to have to translate that. If you want to apply that extinction to a given star, you have to, or if you're interested in deriving, using extinction in a particular passband, you have to go through a procedure like following sort of this formulation here that I've shown to derive what the extinction then is for that particular star, given a particular A0 value. We'll show some online tools at the end of the presentation that helps do that. Right, so where's the data? So inside the Gaia archive, which you can find if you go to the homepage, the Gaia homepage, you'll see, just click on that icon there on the right, and that will take you to the archive. And then after, whether you log in or not, I suggest that if you're going to do queries on the archive, I highly suggest that you register for an account if you don't already have one, so that you can save your queries. And then you'll see here when you go to the search tab and then click on the advanced tab, you'll see this query page come up. And here on the left-hand side are all the tables in Gaia DR3. And there's this subset of tables, astrophysical parameters. You click on that, then you'll see all of the different tables from CU8. And these last two here are the TGE extinction maps. And I'll describe the difference between these two tables here in a moment. So if you click again on one of these plus signs, you can see the different parameters that are in the table. And I'll just go through those now and explain what those are. So first of all, so these are different columns, and each line in the table then is referring to the extinction in a particular heliopix. So the important information here is which heliopix it is, and this gives the heliopix ID. Then there's a column which is the heliopix level. So as I mentioned in the first slide, we provide actually 4 different maps in this first table, photogalactic extinction map, at heliopix levels 6, 7, 8, and 9. So these, as you go to higher and higher heliopix levels, you're talking about smaller and smaller pieces of the sky. Level 6 is about just a little bit less than a square degree. And so to pull out, you need to know both the heliopix ID and the heliopix level of interest that to understand which the values are referring to. And then the A0 is just, again, the median A0, the extinction tracers in that heliopix, the uncertainty of the A0, the min and max values found in that heliopix. Then there's the number of tracers that were used to determine the A0 value. Using so the uncertainty is an uncertainty on the mean A0. So if you want to know the dispersion, you just have to take that uncertainty and multiply it by the square root of the number of tracers used to gives you the standard deviation or the distribution of the A0 values. And then we have this optimum heliopix flag, which I will explain in a moment. This simply lets you know it's either 0 or 1. it's one, it means that heliopix is considered an optimum heliopix. It means that it's the highest resolution in that direction that allows you to have at least 10 tracers. So, which we felt was a minimum to get, confident values for the A0 or the median and uncertainty. And then this status flag is if there's an A0 value, the flag will always be 0. If the A0 value is null, for some reason, the flag will tell you why the A0 value is null. And that only happens for a few percent of the sky, typically near the galactic plane, as you see. So this is the map at level 6. And again, you can see how the white in the galactic plane is where we have no A0 values because we could not find tracers far enough away to be outside to be above or below 300 parsecs from the galactic plane. So we couldn't make a measure there. And then you'll see the rest of the map is showing you that essentially all the rest of the sky is covered at level 6. And now if we go to level 7, the map looks like this. Now we start missing high galactic latitudes. We start missing heliopixes that don't have enough stars to give a measure of A0. And the minimum number of tracers in the heliopix was 3. Okay, so if we had at least 3 tracers, we went ahead and provide an A0 value and an uncertainty. And then at level 8, it looks like this. So we start missing more and more. Of course, as you go, where you do have values, you're getting higher and higher resolution. So as you step in higher level, you're getting the heliopixes at level 7, which are divided into 4 pixels for level 8. And then each pixel at level 8 is divided into 4 heliopixes at level 9. And this is now the map at level 9. You can see that only near the galactic plane do we have enough stars to be able to really make a measure of the extinction. You also see the large and small Magellanic Clouds, which I'll talk about toward the end of the talk, the fact that we can see those in our map. So the fact that we have sort of, you can only really resolve at high resolution some parts of the sky with respect to level 6. One might, of course, want to have the highest resolution possible in any given direction. And this was the idea of the optimum map. So what we essentially did is we came up with a simple algorithm to decide whether a heliopix was optimum. In other words, you couldn't go to a higher level, and essentially fill a heliopix level 9 map with those values for just the subset of heliopixes that are optimal. So just to explain how that algorithm works is essentially if this square here represents a heliopix, we check how many stars there are at the next level. So if this is the level 6, then we have the 4 heliopixes, sub-heliopixes at level 7. And then we check again if there's enough stars to do further division. So if there's at least 10 stars in each of these heliopixes, then we go another step for each of these. And we again ask for, say, this heliopix, which has probably at least 40 stars in it, to have, we will have to have at least 40 stars in it if all of these then at level 8 will be considered enough to be an optimal map. So if there's at least 10 here, we again, in each of these, actually, if there's at least 40 in each of these, then there's a possibility of going to the next level. Okay, if there's not 40, but there's more than 10, then it's tagged as being optimum. And after doing that sort of routine, we have an algorithm essentially that gives only one optimum heliopix in each direction on the sky. Only one level is considered optimum in any given direction. And this is what the optimum heliopix map looks like, which looks a lot like heliopix 6, because at this, just looking at this on the screen, you can't really resolve the pixels, but if we zoom in, then you can see now the sort of the multiple resolution levels that are in the map. So this is the part of the sky that's the Ophiuchus cloud that's fairly close to the galactic plane. These are galactic coordinates that you see on the X and Y axis. And you can see that where the cloud is darkest is where the heliopixels are largest, because we don't have any we have enough stars there. The cloud is blocking out the light, and there's actually very few stars that allow us past the cloud that are bright enough to actually see to get an A0 measurement. In other parts of the map, we have plenty of stars, and we can go to even up to level 9. So that's sort of what the optimum here. This is just for convenience. So even though it's a level 9 map, it's a heliopixels level 9 map, you can see that if you're at the values are populated by just the optimum level at lower resolution. So that the area that I zoomed in on was this area right here, the Ophiuchus cloud. Right. So how to download the table? Now, very simple. If you want to, rather than downloading just a piece of the table, you want to make maps like the ones all sky maps like the ones I just showed, or even explore and zoom in on different areas. The most convenient thing is just to download the entire map. And I made those maps, by the way, in TopCat. And there's probably other plotting routines that allow you to plot heliopix maps. And in that case, it's just convenient to download the entire table. And this is essentially the kind of query that you need to do that. In fact, this query here was one that I did yesterday, essentially that query that you're seeing. And you can see that this table here is 57 megabytes, okay? And the optimum map is about half that size. But I want to warn you should not do this for other tables in the archive, because most of the other tables are huge. And you probably risk it just, reaching your memory limit here, because once you have an account here, your queries can only return so much data. I'm not sure what the quota is, but anyway, for the TGE maps, it's not a problem. They're small enough that you can download the entire. So just some caveats about the map itself. So the first one is that when we were to do validation of our product, we compared to other all sky extinction maps. Here's a plot comparing TGE to Planck. And the dashed line here is the identity. So slope of 1, which is ideally where you would like all your points to fall, of course. If you want to have this, reproduce the same extinctions as Planck. And the solid line is a fit to the TGE data. And you can see that actually the slope is quite good, but there's this small offset. And then the other symbols are showing just doing the comparison, the median values at different heliopix levels. So just showing that there is, because of essentially for a given heliopix, since we're doing a median value of the A0 of the tracers in a given heliopix, and you will typically have more stars where there's less extinction. There is, for the large heliopixes, there's a tendency to bias to smaller values of A0. And this is, you can somewhat see this here as you go to smaller extinction values. As you go to higher levels, you gradually go to higher and higher extinction values. And then there's other biases that start having effect as you get to larger and larger extinction. This becomes a bigger and bigger problem, this tendency to bias, simply because you have more stars where there's less extinction. But this is also part of the reason why you want to use, if you can, go to a higher resolution to try to get around the problem. That really the difficulty in mapping extinction for any map is that you have structure in the extinction at the smallest angular scales, especially as you get toward the galactic. So here, this is just zooming in on that same plot for the at small extinction values, just to make it more obvious this offset that I was talking about. So this red line is the fit, and the dashed line again is the identity. So that's one thing, this offset of 0.09 magnitudes. So you may want to just, if you want to use A0 from the TGE, maybe just simply correct for that. Now, there may be also, I have to say that while we compare it to Planck, there are some parts of the sky that you would probably, not necessarily Planck might not be the best map. I think in lower galactic latitudes where the extinction
Okay, it seems that we cannot hear Ron, you anymore. Ron, can you just try to disconnect and connect or play with your settings? Okay, I think he jumped out. Okay, we give him a moment to see if he's able to connect again. Otherwise, Doug, can you please be prepared to?
Sure. If he can't connect, I'll take over.
Yeah.
Well, I'll take over with my bit because he's got his slides, but I'm sure he'll get back to us.
Yes, I see connected already. I have to let him speak just a moment. Ron, you're here. Okay. Ron, now you are able to unmute yourself.
Okay, yes.
Okay.
For some reason, the connection just dropped out there. Let me put my screen again. I'm not sure why. What was the last thing you heard me say?
Planck, not optimal.
Oh, okay. Okay, so that. Thank you.
Yeah, just shown the 0.09 mag difference.
Right. So let me go back to my presentation mode here. All right. This
one. Yes.
Yeah. Okay. Yeah. Yeah. So this offset. Then I was mentioning earlier in the first slides that we can see the LMC and SMC in the maps. And this was sort of a unexpected thing, right? So we were pulling the giants beyond 300 parsecs from the galactic plane. And in the direction of LMC and SMC, that means that we were also picking out stars in these two neighboring galaxies. So what that means is that in these directions, we're measuring not only the extinction from the foreground extinction from the Milky Way, but we're also to some extent measuring, because there's so many stars, especially at the fainter magnitudes, there's so many stars in these directions are dominated by the LMC and SMC that we're actually measuring the extinction in these galaxies. However, a warning here, even though the variation you see here is probably real, there is a bias in the extinction values in these directions of about 0.6 magnitudes, simply because GSP Fault, when it was estimating this stellar APs, was using a prior that did not include the LMC and SMC. So in these directions, their distances and all the other parameters, many of the other parameters that it was estimating were biased because of that. So it was pulling the stars in closer than they actually are, rather than leaving them out at the distance of the LMC and SMC, since they weren't in the distance prior. So there is a bias in those directions. The TGE map probably should not be used below, say, galactic latitudes of 5 degrees, just because of this problem that I noted in the first slides, that you can't see we don't have extinction measures in the galactic plane because we can't find sources far enough away to be outside the galactic plane. And even in those pixels where we do provide measures, again, we're not really sure that we're confident that, those stars are actually far enough away to give a reliable measure of the total galactic extinction. So use it at your own risk at these very, very low latitudes. The other problem is that the maximum extinction that is in the maps is 10 magnitudes. That's because that was the maximum allowed extinction that GSP fault produced. So if you have a pixel where the A0 is close to 10, it probably means that the extinction measures are reaching the limit. So that should be interpreted as a lower limit of the amount of extinction in that direction. Right, so I think now I will stop sharing and pass this to Doug, who will show some online tools that we've made available to sort of conveniently use these maps. So let me stop sharing and I'll pass it to Doug.
Okay, yeah, thanks, Ron. So I prepared a Jupyter notebook. So to show the Python code, let's see. Okay, everybody can see that. So Ron showed how you can, he explained everything about the TGE maps. He said how you can obtain the maps.
Yeah. I'm sorry, Doug, before you start, can you please enlarge is it possible to have you zoom in? Because not everybody can zoom there.
Okay.
Control plus, I think you will enlarge everything.
Indeed.
Yes.
Okay. Is that better?
Just, yes, perfect. Thank you.
Okay. So with this notebook, I can make it available for download afterwards as well. So yeah, Ron showed how you can get the data from, how you can get the tables from the archive. So this is handy, but as you noticed, the columns in the archive have HealPix ID numbers and not coordinates on the sky. So if you're interested in getting extinction values for a particular line of sight, or even if you want to get the full HealPix map, this is another way to go get it. It does the work for you in terms of ordering the HealPixes on the sky and providing the map. Anyway, so what we did for this is to use the dust maps package from Python. The dust maps package is done by Gregory Green, who, as you might know him from the Pan-STARRS extinction map. Anyway, this package is useful because it gives access to the Gaia TGE map, but also to other extinction maps if you want to have several estimates or compare between them, whatever. The Planck map, for example, is available through dust maps as well. So the first step, of course, would be to download or to install the dust maps package with your Python installation. All the details are available on the link that I provide here. So once you've got that running, we'll just go and import the necessary libraries to do the query of the TGE map. So here I'm just getting some, usual packages. From AstroPy, I'm also getting the coordinates through the SkyCoord class. This enables us to get a list of L and D and convert it to a sky coordinate object. And this is where the dust maps is used. So from dust maps, there's a module called Gaia TGE. We import the Gaia TGE query class. And as we'll be using HealPix, also use HealP. So the HealP here is not necessarily to get the data from TGE, but to display it as a HealPix map. So once all these are installed, we just need to create the query object from the dust maps package. And this is what we will use to then go on and get the values of the extinction and some other values that we can obtain, like uncertainty. We can also query using this object. So it's very simple. You just need to call the class with no arguments, and it'll give you an object as return, so which I just put in the variable Gaia. This is by default the optimum helpix map, which we thought would be what would be most interesting for people to use. If you want to query the map at a different helpix level, this is where you do it. So when you create the query object with the dust maps package, you can specify a different helpix level. So in this case, I did a helpix level 6 object, and I put it in a different variable, Gaia 6, and I can show you how we use these two to get the extinction values at those specific levels. So for a start, I was just going to show you how to get, so you want extinction for a particular line of sight because the object that you're interested in is there. So just create two variables, L and B, for the coordinates that we're interested in, and convert this to a sky coord object using AstroPy. And so once we have those coordinates, we just call Gaia, the object that is the query object, we call it with those coordinates, and it gives us a return value. This return value is the A0 for that line of sight. And this, of course, is the optimum helpix level because I used the Gaia object. The Gaia 6 one will give us the A0 value at level 6. So it's not the same thing because obviously in this line of sight, the optimum helpix level is not level 6. It'll be a different level, which is giving us, therefore, a different value. So that's if you just want one line of sight. If you also want to get a bit more information about that line of sight, you can include a different thing in the call to Gaia. You put in a return flags equals true. This keyword will then give you extra details, not just the extinction, but it gives you it gives you a tuple with two values. The first value is the A0 value, and the second value is another tuple, and this has got three values in it. It's got the uncertainty. It's also got the number of tracers that have been used to get the A0 value, and it tells you whether this is the optimum helpix level or not. So you can see for the optimum helpix map, of course, it returns true. And for the level 6 map, when we queried it, it was this different value. The extinction, the uncertainty is different as well. And the number of tracers used is also different. This, of course, like I said before, is not the optimum level. Okay, so we can do this for one line of sight, as I just showed you, but nothing stops us doing this for several lines of sight at the same time. We can give it a list of coordinates, so a list of L, list of B, and then do the same thing, right? Sky coord can take a single value or a list or an array. And so here coords now will contain all the information for these different lines of sight. And here I query the Gaia object again with these coordinates, and I put the value into A0. And of course, now A0 will contain three values because I've specified three lines of sight. And here I just run through them with a loop and print them out to the screen. So you see these different lines of sight. Here are the different A0 values. So this is if we have different targets and different lines of sight, but maybe what you want to do is say, well, I just want to get the whole helpix map, please. So we can do that too using the same methodology. So it's a little bit more involved. What I specify first here is the level I'm interested in and the ordering. So here I'm using the ring or ordering. So I say nest equals false. This is where the OS that I imported earlier comes into play here, where I just want to specify a file where on my hard drive where I want to maybe save the FITS file. Okay. So once I've got the level, I change that to NSide because help will be using NSides more than helpix levels. It's very simple. 2 to the power of helpix level gives you the NSide. Get the number of pixels, and then use the help package to transform these different coordinates into pixels. Sorry, from other way around, from pixels to the sky coordinates. And then, like I did before, I use SkyCoord to transform this list of L and B into coordinates, and I query the Gaia table again. And I stuff those values into TGE, this TGE variable. This TGE variable will then contain the A0 values in the helipix ordering that I have chosen across the whole sky and at level 9. So this is good for the optimum the map. And that's why I, of course, queried Gaia, not Gaia 6, for example. So I have the TGE map. I can just go ahead and plot that with MolView, for example, and here it is. So in this, I just, I added a min and a max and a color map, but this is, at this point, you do whatever you want. And then I write that map to file. So then I've got the fits file of the helipix map to do whatever I want with later. Okay, so that's how we query using dust maps. I've shown you how to do one line of sight, several lines of sight, or the whole map. Maybe you're interested in getting a map just of one region of the sky. And there are a couple ways of doing that. One is by using the helipix map that you've got here. You can use the help package still to zoom in a specific region using GNOME view instead of MolView. So this you have to specify a center, and you have to also give it dimensions of the size of the map that you want. So here, just for example, I chose a longitude of 0 and a latitude of 15. Chose an angular size of 15 minutes. This is of course, you put whatever values you want in here, and the size of the whole field in degrees. And so for that, there's just a couple calculations to do to get the size of the map in pixels. This is what GNOME view needs to know to have the dimensions of the image it's going to create. I put the center into a little list and then call GNOME view, giving it the map, the TGE map, specifying the center, the resolution, the map size, and any other arguments I want to display the map. So here shows a part of the sky that Ron already showed, but this shows you a way how you can get to it. And you can, of course, change those to get different regions of the sky, different resolutions, etc. Maybe you just want to do this differently, and you can get a Cartesian projection by creating a grid of L and B that you want. So this is the final example I'm going to show you, is you can then just choose a min max longitude, min and max latitude, create the arrays L and B, transform those into 2D arrays of longitude and latitude, and then likewise you just change that to a SkyCoord using Astropy, and then call Gaia once again with those coordinates, and it'll just give you a 2D array of TGE values that correspond to the longitude and latitude that you gave it in as an argument. And here to show that, I use imshow from the matplotlib and give it the extent, et cetera, and here is a TGE map in a Cartesian projection. It just goes for each pixel that I've given it. It'll retrieve the A0 value of that direction, right? So it doesn't care about if it's in a helipix, not in a, what helipix it's in. It'll just say, this is the value in that line of sight at this helipix level, and it'll give it to you. And then you can produce a map like this. Okay, so just to finish, you've seen how to get the A0 values either from the table from the archive or to get it through dustmaps package direct in your Python code. This gives you the A0 value. Now you may want to get it for a different bandpass, and Ron said that there are tools available for that, and indeed there is one that you can get called Dust Approx. All the details are available on the documentation and the URL that I provided here. You can just import that into your Python code as well, and then convert A0 to whatever. It's quite a few bandpasses, and you can also do that for particular sources. Okay, that's all I wanted to tell you today.